Hey everyone. All right, so our goal is to estimate Trump support and kind of characterize the uncertainty around our pre-election estimated Trump support and then compare that to the actual result in the 2016 election to provide some intuition as to whether our polls were kind of systematically biased or to what extent the deviations that we observed were, possibly or not unlikely to be observed just due to chance. Okay, so ultimately, in this kind of inference based on these election polls, the parameter of interest theta is basically the population proportion of likely voters who support Trump, right? So remember that this was a survey among likely voters, and the goal here is to estimate the population proportion, the support for Trump among those likely voters. That's our unobservable parameter in the population that we're trying to make inferences about. Okay, our estimator for that parameter, theta hat, is the sample proportion of respondents who support Trump. Okay, in that ABC News Washington Post poll. And again, our question now is how good is theta hat as an estimate of theta? And since we know the actual election results in the end, kind of to what extent does the deviation between the actual election result and our theta hat suggest that there were some systematic biases, some systematic issues that were basically unaccounted for when computing this estimator. Okay. So how good is theta hat as an estimate of theta? And we're going to look at this from the perspective of, as we mentioned earlier, from the perspective of prior to knowing what the ultimate result will be, right? What we're going to do is we're going to assume a simple random sampling of n voters, and we know the sample size is a little bit 2,200 likely voters across the United States, right? We can then define a random variable, which we're going to call xi, which is equal to 1 if the ith respondent supports Trump and equal to 0 otherwise, right? So this is our dichotomous indicator that indicates Trump support for each individual respondent in our survey, right? The data generating process is then a binomial distribution, and if you are not quite sure exactly how the binomial distribution looks like, make sure to go back to our video on probability distributions where I talk a little bit about the binomial distribution. This binomial distribution has a success probability p and size n. So we have n trials with success probability p, where again p is the population proportion of likely voters who support Trump. Right? Then our estimator for this population is the average or the expectation across, or the average across our sample. So that's x bar, and x bar is just another way of writing the average 1 divided by n times the sum from I equals 1 through n of all xi's, right? So we're summing all xi's together, which are either 1 or 0, divide by the number of observations, and that's the proportion of Trump supporters in our sample, or short x bar, okay? That means in this specific example, our population parameter that we're trying to make inferences about is p. That's the true kind of success probability, or the true kind of proportion of likely Trump voters in the population. And our estimator for that parameter is theta hat, and that is just x bar. That's the average of the average Trump support in our sample. Okay. So after we kind of set up this this basic framework with our estimator and our population parameter, the first question that we want to ask, or that we can ask, is how well would x bar behave as the sample size increases, right? So suppose we had a larger sample size, or our sample size would increase to infinity. What would happen to kind of our parameter? Sorry, not our estimator x bar. And given the law of large numbers, which we discussed in the previous weeks, what we can say is that x bar, as the sample size increases to infinity, x bar approaches the true population parameter p. And this is what we call consistency, right? So our estimator x bar is consistent in the sense that increasing the sample size will bring it closer and closer and closer to our true population value, p, okay? And this can be shown using the law of large numbers. Again, make sure to check out those videos in the previous weeks. So this is nice. We already know now, or we can say that if we had a very, very large sample, or the larger our sample is, the closer and closer we get to the true population value that we want to make inferences about. But of course, we're not able to, sample a, infinitely large sample or a full sample of the entire population. So the question is, how large is large enough in terms of how large does the sample have to be in order to provide a reasonably accurate estimate of our population proportion that we're interested in, right? And in order to answer that question, we can think about how would x bar, how would our estimator behave over repeated data generating processes, right? So given our sample size, how would x bar look like if we repeated our sampling procedure again and again and again, basically computing a bunch of x bars and then looking at the distribution of x bars across those repeated data generating processes, right? And that's what we mean by looking at the sampling distribution of our estimator, okay? So this is always kind of a hypothetical scenario that we're talking about, right? We're talking about repeatedly conducting a survey under the exact same conditions many, many, many times. And then we're looking at the distribution of our estimator across those repeated data generating processes, right? So in expectation, and we talked a little bit about biasness and unbiasedness in the context of OLS in previous weeks. In expectation, what we can say is that the expectation of our estimator, so the expectation of x bar, is equal to our true population parameter p, and that's exactly what we mean by unbiasedness, which means on average, over repeated sampling procedures, over repeated data generating processes, in expectation, our estimator is equal to the true population parameter. So it is unbiased, okay? And then in addition, so we know that in expectation, over repeated sampling procedures, in expectation, the x bar is equal to the true population parameter. But the next thing is to look at the distribution. So how much does the x bar, how much does an estimator for one individual sample, to what extent does the distribution of that estimator across repeated samplings change between samples, okay? So that's what we mean by the sampling distribution of x bar, okay? And we know that x bar is a binomial random variable, and so we can directly kind of specify the variance and standard deviation of that sampling distribution, right? The first, let me move myself a little bit here because this is not 0. All right, we're back. So we can first compute the variance of that standard deviation. The variance of that sampling distribution, right? X bar is our estimator. We compute one x bar for one sample. Now we're in a world where we hypothetically repeat our sampling procedure maybe 1,000 times. We have 1,000 surveys rather than just one survey. And for each of those surveys, we compute x bar. And then we look at the distribution of those x bars across all those surveys, right? Now, what is the variance of that sampling distribution? What is the variance of those x bars across all our samples? We can directly just plug in x bar here. And we know that x bar is actually just the average of our xi's, right? The sum of all the xi's divided by n. And remembering kind of basic rules of how to deal with variances, we can pull out this 1 over n. That's a constant, so that's 1 over n squared, and we can put that in front of the variance. And now we said that xi, this is a random sample. Those are independently and identically distributed. This is an IID variable, so it's independent and identically distributed, right? So two variables that are independent of each other, if we look at the variance of the sum of those variables, that's equal to the sum of the variances, right? So we can also kind of pull out that sum and express this as 1 over n squared times the sum of all the variances of xi. Okay, right? So all we're doing is we're plugging in our x bar, which is just the average, and then we're using our basic rules of how we deal with variances. We pull out our 1 over n, and we pull out the sum because the variance of a sum of independent random variables is equal to the sum of the variances. And that's what we have here. And we know the variance for xi because it's a binomial random variable. And the variance of a binomial random variable is, of course, p times 1 minus p. Right? Again, make sure to check out the previous video on binomial random variables. And that would be divided by n square. Okay. I think, yeah, there's a little square missing here, but that's fine. I'll fix that in the in the slides. Then next we can compute what is called the standard error. And what we mean by the standard error, that's the estimated standard deviation of the sampling distribution, right? So again, keep in mind that whenever we talk about the standard error, we're talking about the distribution over repeated samples, right? We have our estimator x bar. We're looking at that distribution over repeated, hypothetically repeated sampling procedures. And the standard error is just the standard deviation of that distribution across repeated samples, right? So it's just the square root of the variance that we just talked about, the variance over x bars over repeated samples. Okay, so basically all we have to do is take the square root of the fraction that we just computed. That's p times 1 minus p divided by n. So we have 0.43 times 1 minus 0.43, which is the predicted Trump support, divided by 2,200, and that's approximately 0.011. So that's the standard error of our sampling distribution. In other words, that's the average deviation in x bar across repeated samples basically from the true population parameter. Right? We know that in expectation our estimator is equal to the true population parameter, but on average it deviates by 0.011. Okay. All right. Based on this, we can now, based on this standard error, so the estimated standard deviation, we can now compute the confidence intervals for our estimator. I'm going to take a quick break here and then get back to computing these confidence intervals.